So series and sequences is essentially series is talking about the sum of a sequence, and the sequence is just an ordered list of numbers. So 1, 2, 3, 4, 5, 2, 4, 6, 8, you know, it can be really anything. In Specialist, we talk about two different types of sequences. So we talk about arithmetic sequences and geometric sequences. Arithmetic sequences are to do with adding, and geometric sequences are to do with multiplication. So how do these sequences work? So first of all, let's talk about arithmetic sequences. So arithmetic sequences are essentially when the successive terms involved adding something. So we're adding d on each time. So we're going 2, 4, 6, 8, so that we're adding 2 each time. Or if we're going 1, 5, 9, we're adding 4 each time. Or if we're going 1, 5, 9, not 1, 4, 9. If we're going 1, 7, 13, or something like that, we're adding 6, yeah? Like, we can add different terms each time, and the d thing will be the thing that's changing. And our tn minus 1 is going to be how we represent it. Importantly here, we need to tell them what term we started on in terms of the recurrence relation, just because if we don't tell them what term we actually start on for here, we don't really have any term to start on. So we always need to tell them what a is, and a is the first number in the sequence, or we need to tell them what t1 is, essentially. Okay, so if we write, so this is called a reoccurrence relation, and this is called the rule, right? So if we want the rule so that we're able to kind of pinpoint exactly, so if we wanted to be able to find the fifth term straight away, we would need to find a rule for it rather than doing this, because if we wanted to find the fifth term using this, we'd need to find the fourth term, and then the third term, and the second term, and then kind of going backwards, right? So because we are not very keen on doing that, we can just use this instead to find the sequence. And essentially it's just a rearrangement of the letters and the rearrangement of the terms here to kind of form this. And A represents the first term in the sequence, so it represents your T1. And D is that common difference, so 2, 4, 6, whatever. So the difference in that sequence would have been 2. Cool. So if we want to find the 12th term of this sequence, so the first thing that we want to do is figure out a rule for this, right? So we want to compare what's happening in between each of these. So we note that it's adding 4 on 4, or adding 1 essentially. So 4 on 4, 4 on 4. So therefore we can derive that d equals to 1. A would equal to negative 1/4, right? So therefore our Tn would be equal to a plus 1n minus 1d, which is our equation for it, and we just plug everything in. So we get 1/4 plus n minus 1, which is n minus 1 still, times by 1. So we'll end up with 1/4 plus n minus 1, so we'll get that this is negative 5/4 plus n. And we can try for different n values. So for the first n value, that would equal to 1, equals to 1/4, looks good. N equals to 2, 2 plus 5 on 4 is going to be 3 on 4, looks good. 3 plus 5 on 4 is 12 on 4 minus 5 on 4, so that's going to be 7 on 4, like here. So we're happy with that as well. Alright, so then we can kind of, now that we're happy with the actual sequence, so it's always good to double check throughout what you're doing. So now that we're happy that we've double checked and looked and made sure our rule is correct, what we can do next is actually sub in. So now we're looking for n12, so that's going to be negative 5 on 4 for us plus 12. So negative 5 on 4, and we can convert that into fourths as well, so that's 48 on 4. So we'll get that 43 on 4 is equal to 12. So therefore 12th term is 43 on 4. Cool. Alright, next one. So this is kind of a bit of a reverse one, because they've given you the terms, but they've only given you really specific terms, right? But once again, we know that Tn equals to a plus n minus 1d. And once again, we can try and sub those in. So there's kind of two ways of going about this, and one of the ways is just finding the common difference first. You can either do simultaneous equations from the get-go, or you can just use like the common difference. So if we look at these two terms, right, if we go 62 minus 22, that's going to be 40, and that's going to equal to d times by 15 minus 5, right? That's going to equal to 40, because that's the difference of how many terms. So we'll get that 10d will equal to 40, and therefore d will equal to 4. So we can sub in here that a plus n minus 1 times 4 is what's going to actually give us the value, right? Okay, cool. So therefore we can now try and find what this is, and we can sub in either one of them. So let's talk about t to the power t to 5. So that will be a plus 5 minus 1 times 4, and that's equivalent to 22. So 22 is equal to a plus 4 times 4, so 16. So a for us should be equivalent just to, so that should be equivalent to 6, right? Okay, so therefore we can get the equation Tn will equal to 6 plus n minus 1 times 4. So we'll get that this is going to be 6 plus 4n minus 4. So we'll get that this is going to be 4n plus 2. And we can kind of check here as well. So if we times 15 by 4, we'll get that that's 60 plus 2 should be 62. Alright, so let's find T100. So T100 is going to be 4 times 100 plus 2. So we'll end up, that's going to be 4. It's going to end up becoming 402. Alright. Okay, so if we have an arithmetic sequence which goes like this, so i.e. we have a, then 2a, then a squared, right? So we have this and this and this. So we know that the difference between these two is a, and the difference between these two should still be a, right? So therefore we can say a squared minus 2a is actually going to be equivalent to a. So that's because we know that the difference should be there. So a squared minus 3a is going to be equal to 0. So therefore we'll get that a minus 3 will equal to 0. So therefore a will equal to 0, or a will equal to 3. But a cannot be equal to 0, because if a is equal to 0, you're not really going to have an arithmetic sequence, right? As a is common difference. So therefore a will equal to 3. And we can kind of see that. So we have 3, 6, 9. And that's why a squared and a. Okay, let's talk about a bit about geometric sequences now. So geometric sequences is the other half of sequences that we chat about. So essentially a geometric sequence is, instead of us plussing on terms each time, what we're doing is now we're kind of timesing the terms each time, right? So instead of doing the plussing, we're timesing instead. So now instead of having, we're going to have Tn equals to r Tn minus 1, so as in we're timesing the previous term by something to get the next term. Once again, it's more useful to have the rule for it, because that means we can just grab, we can say we want T100, we want T50, we can tell what that number is straight away. So once again, we'll have the first term, because we need to know where we're starting, so we need a first term, so a, and then we have r, which represents the common ratio, so how much I need to times by each time. Cool, so let's chat about that. So now we have to figure out what's going on from here to here to here to here. So we can figure out that that's actually timesing by root 2 and timesing by root 2. So therefore we can kind of identify that we'll have r will equal to root 2 and a will equal to root 3, right? So that we're going to apply this to our formula. So Tn equaled to our a times our n minus 1. So that's going to give us root 3, root 2, n minus 1, right? So you can, you can expand this further if you wanted to, but I feel like it's not really worth it. You can kind of just leave it like that if you want. And we can just make sure to check. So if we subbed in 1 minus 1 is 0. That should just be 1. That looks good. If we have 2 minus 1, so it's root 3 times root 2, so that's root 6. Looks good. If we had 3 minus 1, so that's root 2 squared, so we'll have 2 root 3. So it looks good. So we've done our checks, and now we can move on to actually subbing it in. So we'll have root 3 times root 2, 12 minus 1, which means we'll have root 3 of 2 to the power of a half times 11. So we'll have root 3, 2 to the power of 11 on 2. So therefore we'll have root 3, 2 to the power of 5 times 2 to the power of a half. Okay, so why I did it that way is because I find this will be easier for us to actually write out at the end. So the last one will be left over, so we know that we'll have a root 6, and then 2 to the power of 5 is 32. So essentially we can write T12 is equal to 32 root 6. Okay, cool. So once again, they've given us rules instead of what we're they've given us just two separate terms to work with. So we know that Tn equals to Arn minus 1. So for this one, we can try the simultaneous equation method, since we talked about the common, talking about dividing or timesing by the common difference in the previous one. So, or more like we talked about the common thing that we're doing, we did it with the common difference and worked it out by there. And for this one, you could do it via a common ratio just by dividing the two and then making that equivalent once again. But we should try different methods for things just to display it. So if we sub in T10, that's going to give us A times R to the power of 9, right? And that's 512 is going to be equivalent to A R to the power of 9. If we sub in T15, that's going to be A R to the power of 14. So we'll get that 13684 is equivalent to A R to the power of 14. Now, we have equation 1 and equation 2, and what we can do is just try to get rid of the a's, so we can try and divide 1 by 2. So, 2 by 1, sorry. So that the bigger number is divided by the small number. We get 512. This is equivalent to just the a's cancel out, and we'll have R14 over R9. Okay, so if we look into this, we can try and figure out how many times this goes in. I'm predicting this will go into 3 times, because I can see if I times this by 3, it would be 15 something. So I'm going to try that. So 15 times 3, so I'll get 6 here, I'll get 3 here, and then I'll get 15 here. So that's not quite as big as I need. We can also do a bit of just long division. You can either decompose it or just do a bit of long division. So we can just do a bit of long division, I reckon, to simplify it a little bit. So 512, 16384, right? So we talked about how this part 512 wouldn't go into that. If it went into that, we would timesing it by 3. So if we times it by 3, once again we would have gotten 6315, right? So we can say, all right, so that's 2, 0, 1, not 4, right? Okay, so 2014 is that just times 2, so 32. You can see that's that times 2, right? All right, so therefore we know that's going to be 32. So 32 would equal to R to the power of 5. R to the power of 5, so if we fifth root 32, 32 was just 2 to the power of 5, so R would just equal to 2. Okay, so then we can sub it back in to one of these to actually find what A is. So now that we know that's 2 to the power of 9, so that's going to be 512 equals to A to the power of 9, and 2 to the power of 9 is actually 519. So A will just equal to 1. And we can check that one more time. So I know that 2 to the power of 10 is equivalent to 1024. So therefore, if we times that by 2 again, we'll get 2048. And then 2 again, we'll get 4. So that's 11, that's 12. So that will be 4. That's 11, 12. So 4, 0, 9, 6. And then 13 would be 8. So that's 12, 1, 9. And then we can see that one would double into that. So we're happy with that. Okay, cool. So then what we're going to have is, so we now know that our equation Tn is equivalent to 1 R. Let me just rub that out. So it's equivalent to Arn minus 1, and A is 1 and R is 2. So we can just put that in. So it's just 2 to the power of n minus 1. So 2 to the power of 51 is just going to equal to 2 to the power of 50. I'm not going to work out what that is because I think it's going to be a waste of both of our times, right? So just know that it's 2 to the power of 50. You can probably plug that into your calculator. Alright, so that's the sequences itself, but let's talk about the sums of the sequences. So what I want you to remember is just have these formulas in your notes somewhere. So the sum of a sequence for the arithmetic sequence is derived from the position that it's the first term plus, you can also write it as the n over 2, a1 plus l, where l is the last term that you're working with. so as in a to the power of n. It can also be written like that. The geometric sequences, this is the general for this fifth term, for the nth term, sorry. But if you want the infinite sequence, a really important condition is that r has to basically be a fraction, and r evidently can't be 0 because otherwise it's not really going to be a ratio, but r has to be a fraction because then it kind of dwindles into nothingness at the end, and then you kind of get the equation that it's a over 1 minus r. Okay, cool. So let's kind of work through these a little bit together. So if we consider this sequence, a1 plus a squared plus a cubed, and tn plus 2 equals to tn. So we can kind of do that a little bit. So tn plus 2, right, is going to be, so if we just kind of pick a point, and that's t1, that's t2, that's t3, right, tn plus 1, we can kind of pick a point. So therefore tn would equal to let's say t3 would equal to t1 plus t2, right? That works. So therefore we can plug the points in. So a squared would be equivalent to a plus 1, right? So a squared minus a minus 1 equals to 0. So therefore you'll get that a will equal to 1 plus or minus root 1 squared minus 4, 1 negative 1 over 2. So a will equal to 1 plus or minus root 5 over 2, which is the golden ratio. Just for your information. Cool, awesome. All right, so now they want us to do all the arithmetic sequences and find the sum. So the equation for the sum of n was equivalent to n over 2 2a plus n minus 1 times d. So therefore we would have n over 2 2a, so that's 2 times 2, plus n minus 1d. So d, we can see 3, 3, 3, 3. So that's times by 3. So we'll have n over 2, 4 plus 3n minus 3. So we'll have n over 2, 3n plus 1. All right, so then we can sub in S15. So S15 equals to 15 over 2, 3 times 15 plus 1. So that's going to be 15 over 2, 46. And that's going to be 15 times 23. So 15 times 20 would be 300. 15 times 3 is 45. So we have 345 as our answer. Cool. Alright, so next is geometric sequence. So we want to find S10 and then S infinity. So Sn for this one, remember it's equivalent to a 1 minus Rn over 1 minus R, right? So we can say that a is going to be 1 here, 1 minus Rn, so 1 minus, we can see common difference is a half across, so it's going to be a half to the power of n. That's all going to be 1 minus 1 half, right? So we can see that's going to just be 1 minus 1 half n over 1 half, so it's going to just be 2, equivalent to 2 times 2 to the power of 1 half to the power of n. So then if we want to find S10, we're going to have, this is going to be equivalent to 2 minus 2 to the power of a half times 10. Once again, we know that 2 to the power of 10 was 1024, so we'll get that this is going to be 2 times 2 over 1024. So that's going to be 2 minus 1 over 512, so that's going to be 511 over 5. So it's going to be 1024 minus 1 over 512. So it's going to be 1023 over 512. Cool. Okay, and then S infinity. S infinity is just equivalent to a over 1 minus r, and we can see that because this is a half, it's between the points of negative 1 to 1, so it's a fraction. So therefore we'll have here that this is going to be a, so 1 over 1 minus r, 1 minus a half. So our ultimate goal is to get to 2 essentially, which you can see this is already pretty close. But it'll get closer and closer and it'll probably never reach it.